it's a good time to begin.
Okay, so just a few words of welcome. So first of all, I'd like to acknowledge the real organizers of this meeting, most of whom you can see, Nobuchika Okada, Anish Ghoshal, Ogumia Shvechevska, Mark Levitsky, and Kaiser Shafi. So we're very pleased that you're able to join us even remotely. So I think we all understand how gravitational waves have opened a new window on astronomy with many exciting astrophysical discoveries in the last 5 years. But the purpose of this workshop is to somehow go beyond that and analyze how gravitational waves can be used to explore possible fundamental physics beyond the standard model and beyond conventional GR. So of course, there's already been quite a lot of work on this, which is going to be reviewed in the course of this workshop. And I'm sure a lot more interesting new ideas will come up in the coming days. Excuse me. So the purpose of this workshop is to bring together experts in particle physics, cosmology, gravitational wave community, general relativity, to discuss all these exciting prospects opened up by the discovery of gravitational waves. So I'm not going to say any more. I hope this is going to be an extremely lively workshop. And without more ado, I will hand over now to Jose Miguel No, who has kindly agreed to chair the opening session. So, oh yes, I forgot to say, everybody is welcome, even Italians. Thank you. Sorry, we can't hear you, Jose Miguel.
No, we can't hear you.
Now you can hear me.
Yes, yes.
Yes. Sorry, I mean, we have a 2-month-old baby at home, and apart from the craziness, I guess like normal things start to not work in this kind of situations. Anyway, thank you very much. We start our first session, and our first speaker of the topological defect session is Hitoshi Murayama. Please, when you are ready.
Yeah, I'm ready. I'm just trying to share the slides. Let's see. Looks kind of slow. I don't know why.
Here it comes.
Yeah, it's coming.
Is it coming? Okay. Do you hear me okay?
We can hear you okay. Give us a sec. Do you see the slides?
I don't see the slides yet. It says started screen sharing, but I don't see anything.
Somehow it's taking time. Is it now? You can see now?
I don't see them yet.
Oh boy.
Here it
Why
is.
is that so slow?
Now they just appeared.
Oh, did it just appear?
Yes.
Okay, so let me get started then. So the title of my talk is Neutron Mass Leptogenesis Gut. And this is actually the first talk in the topological defect session, even though I have to apologize that my main interest for this talk is really baryogenesis. And I will also touch on something that doesn't have anything to do with the topological defect. So the motivation is clear. So it's about the cosmic mysteries, about the cosmic pie chart. We don't know what dark energy is. We don't know what dark matter is. We think we know what baryons are, but we don't know why they exist. So that's why we have to think about the origin of the baryons in the universe, namely what created the asymmetry between the baryons and antibaryons. And you all know the Sakharov's three conditions to explain this mystery. We need to have baryon number violation, we need to have CP violation, and you need to have departure from equilibrium. But we have very little clue right now where and when all of these ingredients have been satisfied to create a baryon asymmetry of the universe we rely on today for us to exist. And it's actually a single number. And I have to say there have been too many theories for single number. But nonetheless, there had been two major paradigms to explain the origin of baryon asymmetry. One has to do with the leptogenesis, namely that the origin of baryon asymmetry is closely tied to the origin of the neutrino mass via seesaw mechanism. But another idea has to do with the idea called asymmetric dark matter, that somehow the baryon asymmetry and dark matter are closely related to each other. So I'd like to touch upon both of these ideas in the rest of my talk today. So let me get started with this idea that somehow the seesaw mechanism as the origin of neutrino mass is tied to the origin of the baryon asymmetry. And this tie-in can in principle be probed by the gravitational wave to the topological defects. And that's the idea I'd like to talk about for the first half of my talk. And everybody knows that the neutrino mass has been discovered in neutrino oscillation. And this has been already awarded the Nobel Prize in Physics. We know the neutrinos oscillate in atmospheric neutrinos. And this has been, of course, a great excitement. One of the first evidence for physics beyond the standard model we have found experimentally. And I was so excited that I myself have been involved in neutrino experiments called CAMLAN, which actually verified the neutrino oscillation in the neutrinos coming from nuclear power plants in Japan, which were operating before the Fukushima incident, by the way. And now we can measure the background extremely well. So the CAMLAN experiment really showed that neutrinos do oscillate and they start to disappear first and then reappear, disappear again, and reappear. So we have actually observed these two cycles of oscillation in actually real experimental data. And so this has been actually a great excitement for myself being involved in the experiment, even though, as many of you know, I'm basically a theorist. But anyway, so this is what happened. And we know that neutrinos have mass, they do oscillate. And that's why we can actually think about the origin of the baryon asymmetry. And now I do see that the slides progress actually very slow. I don't know why. So let's see if I can get better. So what we have learned, though, is that neutrinos, the other masses of the quarks and leptons, neutrino masses are at least 6 orders of magnitude lighter and possibly even more. So the lightness of neutrino mass people to postulate some connected origin to the grand unified theory. So why is the neutrino mass small? And one thing we learned from experiments that the neutrinos are all left-handed. That's a famous experiment by Goldhaber and company, which really established the spin of the neutrino, which was an amazing experiment back in the 50s. And this was okay, as long as the neutrinos are always moving speed of light, namely massless, because the being left-handed is a frame-independent observation. But now that they have mass, the handedness of the neutrino is actually frame-dependent, because the neutrinos cannot go with speed of light now that they have mass. In principle, young people like Anish can run faster than neutrino, and then he can look back at the neutrino and observe the neutrinos going backwards, but still spinning the same way, namely that the neutrino looks like a right-handed fermion. That poses a problem. So one way to solve this problem is that to introduce a genuinely new degrees of freedom, namely right-handed neutrinos. But what many theorists, including myself, prefer is going a little bit more economical. Namely that we do have to introduce right-handed neutrinos so that we can write the usual Yukawa couplings that are between the right-handed and left-handed neutrinos. But normally you would think that the size of these Yukawa couplings are sort of comparable to other Yukawa couplings we have in nature, like the mass of the electron. And if that's the case, the mass of the neutrino will be way too heavy. Your seesaw is down. But the idea here is that the right-handed neutrino, if you introduce this way, is actually a singlet under all standard model gauge groups, and therefore it can have a mass without relying on the Higgs mechanism in the electroweak theory, and therefore its mass can be much, much higher than the electroweak scale. And if we introduce such a very heavy mass scale, then that would actually tip the balance of this seesaw, because that would bring in this big diagonal component to the mass matrix of the neutrino. And that's a big mass that's shown on this seesaw. And the seesaw, of course, goes the other way, given this heavy mass. And that actually corresponds to having a very tiny eigenvalue of the neutrino mass matrix, which is suppressed by this heavy mass scale capital M of the right-handed neutrino. So somehow the heaviness of the right-handed neutrino energy scale is related to the smallness of the observed mass of the neutrino, as evidenced in neutrino oscillation experiments. And that's the idea of the seesaw mechanism. So when you actually look back at this, the neutrino that is moving backwards now, you're actually staring at an anti-neutrino instead, because the neutrino actually turns into a Majorana fermion in this case. So the idea that this might be connected to the origin of the baryon symmetry of the universe is that this heavy right-handed neutrino must have been produced in an early universe, even though they are very heavy. But right after Big Bang, there was enough temperature to create them. And those right-handed neutrinos would eventually decay. So being a Majorana fermion, they can decay both into the regular fermions and regular anti-fermions, namely neutrinos and anti-neutrinos in this case. And at the tree level of this reaction, the decay rate will be 50-50 into the neutrinos, namely the matter sector, versus anti-neutrinos, namely the antimatter sector. But when you pick up the interference between the tree level diagram and one loop diagram, especially its imaginary part, that can create an asymmetry between these decay rates that would actually make the right-handed neutrinos, let's say, decay into normal neutrinos by 49% and anti-neutrinos by 51% instead. So this kind of the direct CP violation, of course, is now observed in the K-on physics by epsilon prime of epsilon, and also to some extent in B physics. So this is actually known to happen in Mother Nature. So if the right-handed neutrinos would do the same thing, then when they decay, they would implant asymmetry between the neutrinos and the anti-neutrinos, and therefore lepton asymmetry. So the fact that this may be coupled to the baryon asymmetry, it has become a dominant paradigm in neutrino physics, but at the same time, it's actually groped to a very high energy scale. But being coupled to high energy scale actually makes this theory notoriously difficult experiments to approach such energy scale directly. The reason has to do with the baryon asymmetry is actually known in the standard model physics via the electroweak anomaly. Namely that if you have the Dirac equation in the thermally fluctuating plasma of the W field, then every left-handed particle that will couple to W boson, which is now fluctuating as a classical field in the plasma, would actually oscillate back and forth in the thermal fluctuation. So all the energy levels go up and down all the time. And what we learn in graduate school is that all the negative energy states of the Dirac fermion have to be occupied, or the positive energy states have to be left vacant to define the ground state of the system. And all these negative energy occupied states are going up and down in energies all the time in this thermal fluctuation. But when the fluctuation becomes large enough, sometimes this fluctuation can go all the way to the extent that all these negative energy states will now fluctuate, and one of them will stick above zero, namely that you can find now in one positive energy state is occupied, and you will say, aha, there's now a particle there. And this phenomenon would happen to all left-handed particles because they will couple the same way to W field, namely that the same thing would happen to all quarks with 3 colors and also to the leptons. And therefore, quark numbers for 3 colors and lepton number would change the same way in the thermal fluctuation, and hence changing the baryon number and lepton number by the same amount. So if you do have the lepton number implanted by the decay of these heavy right-handed neutrinos, then the universe would find sort of compromise by minimizing the free energy between having baryon number versus lepton number. So they settle somewhere in the middle to minimize the free energy. So what used to be the pure lepton number at the beginning would now turn into a mixture of the baryon and lepton numbers. Hence, you generate asymmetry in baryons. So that's a scenario called the leptogenesis. And in fact, this scenario would satisfy all three conditions of the Sakharov, namely the baryon number violation exists because the combination of lepton number violation due to Majorana's of the neutrinos, plus this electroweak anomaly that would preserve B minus L, but to violate B and L individually, together, they would violate the baryon number. So that's actually a known effect in the standard model. It would also violate CP because the Ikawa couplings of the neutrinos can have CP phase and therefore can violate CP, leading to this difference in the branching ratios into lepton and anti-lepton final states. In this case, even 2 generations is sufficient to have such a CP phase. And you also have the departure from equilibrium because the right-handed neutrinos are typically assumed to be very weakly coupled. The Ikawa couplings are very tiny. So once they're produced, they hang on until their lifetime comes and eventually would decay. So that will be out of equilibrium decay, and therefore it would be departure from equilibrium. So all these conditions are satisfied, and therefore at least this scenario is eligible to produce the baryon asymmetry of the universe as we rely on existence today. And many people have looked into this scenario in a quantitative fashion. This is actually a famous review article by Barry, Plumacher, and Buchmüller, and they panned out this parameter range where successful baryon asymmetry can be generated for the range of the neutrino masses, which is kind of reasonable from the point of view of the observed scale for the neutrino oscillation measurements. And then it requires the energy scale of the right-handed neutrino to be somewhere between 10 to the 9 GeV to 10 to the 15 or 16 GeV, somewhere close to the grand unified scale. So we are talking about this very high energy scale, and that actually put us in a difficult situation. How do we exactly test it? So the only thing we can imagine to test it directly with the GeV collider, if you scale up the currently existing technology to build such a Milky Way galaxy, so that would not only require international multi-agency collaboration in addition to that, so that would be out, we expect that to happen at least in my lifetime. So how do we test this kind of idea? Then cannot rely on this direct test using the accelerator experiments. So we have to rely on much more on circumstantial evidences. And this is the approach I call the archaeology. And archaeology means you're not going back to the history to recreate what happened in history, but you dig up enough of the fossils or artifacts, and if they line up to tell you the same story, you start to buy into that story. So that's the idea of archaeological evidences, whether we can justify leptogenesis kind of idea that way. And people talked about at least 3 circumstantial archaeological evidences for leptogenesis, like neutrinous double beta decay that might establish Majorana's of the neutrinos, CP violation, neutrino oscillation, which may be tested occurring at T2K and the nova, and eventually at a hyper K in the dune, both in Japan and the United States. And there could be also some other circumstantial evidences if we are lucky enough to have new particles below 100 TeV scale, that neutrino oscillation physics can also impact lepton flavor violation, which may be tested, for example, in mu2e experiment at Fermilab. So that's the approach I call archaeology. So if we actually have enough of these circumstantial evidences, maybe at some point we start to believe in this idea of the leptogenesis. So more circumstantial evidences there are, of course, the better. The question is whether you could have some more circumstantial evidences than listed actually here on this list. So they're looking at this energy scale of interest from 10 to the 9 GeV to 10 to 15, 16 GeV. It's interesting that this is, of course, incredibly high energy scale, but still not quite there at the Planck scale yet. So if you think that this range is the relative mass scale for the right-hand neutrinos, it looks like the right-hand neutrino doesn't have any quantum numbers to forbid their masses, but why then is not as heavy as the Planck scale? So then it's actually reasonable to think about some symmetry that would forbid the mass of the right-handed neutrino to begin with. That's why they are not up the Planck scale. It's substantially lower than that. But there's a period of symmetry breaking, some kind of phase transition, like in Higgs mechanism in the weak theory, that would induce the mass scale for the right-handed neutrino via the phase transition. And if that scale of the right-handed neutrino is relevant for leptogenesis, of course, that has to happen below the inflation scale, which may be somewhere up to 10 to the 16 GeV scale and so on. So we need to have some phase transition below the inflation scale that would generate the mass of the right-handed neutrino, and therefore that will lead to the generation of the baryon symmetry afterwards. And if you think of the phase transition, then you have a hope that it might also lead to yet another potential circumstantial evidence, such as the gravitational wave. The simplest scenario you can come up with along this line of thinking is that they may be actually gauged B-L symmetry. So if you have the U1 B-L gauge symmetry, that would forbid the mass of the right-handed neutrino because that would violate B-L symmetry. But once the U1 B-L symmetry is broken by Higgs mechanism, then this mass then becomes allowed, and therefore the phase transition can lead to a mass of the right-handed neutrino. So we can think about this example as a simplest example of that. So if we have a Higgs field that would condense and lead to the U1 B-L breaking, and if that Higgs field would couple the right-handed neutrino with the lepton number 2, then it does. So in this case, you have a B1 U1 gauge symmetry that breaks to produce the mass of the right-handed neutrino network of cosmic strings. And cosmic strings are known to behave in a nearly scale cosmic the string network. And so the way the network simplifies itself to remain scale invariant actually requires energy loss from the string network into some form of the energy loss. And that could be gravitational waves when all the particles coupled to the string network are heavy, unlike in the case of the global symmetry, which might end up with, for example, production of axions instead. So this kind of mechanism can lead to a stochastic gravitational wave background. And more experts will be talking about this after me, so I would actually keep this discussion a minimum. So the idea is that cosmic strings get generated by Kepler-Zurek mechanism from the symmetry breaking. But this network keeps simplifying itself as more strings come into the horizon because the energy of the string is proportional to length. Any complicated network would have a substantial energy density. So by stretching out the strings and simplifying itself would minimize the energy on the way of its evolution. And that simplification would require reconnection and the cusps and loop disappearings. And all these processes can in principle go to the gravitational waves. So what we pointed out in the paper is that if you think of any new gauge symmetry that would forbid the mass of the right-handed neutrino as a cause of the gauge symmetry, and is normally free without any additional fermions, and doesn't lead to magnetic monopoles that would contradict with the current cosmology within the minimal rank requirement, then it turns out that there are only 8 consistent scenarios along that type, based on various forms of the gauge symmetries. And it turns out that 5 out of the 8 possibilities would lead to the network of cosmic strings because of the topology of this symmetry breaking. So it turns out that having a cosmic string associated with phase transition that would produce the mass of the right-handed neutrinos is actually fairly generic. And it's not this actually a plausibility argument is not the necessary condition, but nonetheless, it's quite plausible to think of cosmic strings come from the phase transition that would generate the mass of the right-handed neutrino, and hence leading up to the leptogenesis, and at the same time with a seesaw mechanism. And as I argued before, the typical energy scale required for this is somewhere between 10 to 9 GeV to 10 to 16 GeV. And if you do have cosmic strings tied to this kind of energy scale, and combining the currently the running experiments and currently designed experiments, and also with the future missions being planned, then the emissions and experiments combined together, it will basically cover the entire range expected for the energy scales for the cosmic string network from 10 to the 9 GeV to 10 to 15 GeV by combination of all these future experiments and missions. So it turns out that expecting this kind of gravitational wave signal is quite generic by future experiments and giving us a new circumstantial evidence in a sense of archaeology as the common origin of the neutrino mass and baryon asymmetry. And I think Kai will talk more about this via the supersymmetric hybrid inflation. In this case, the hybrid inflation would actually end the inflationary era by producing a wave in a field that break U1B minus cell, at the same time also producing a U1B minus cell string network. And it turns out that this kind of scenario prefers relatively high scale of the B1B minus cell breaking. It seems to be already excluded also timing array. But it turns out that if you actually embed U1B minus cell into grand unified theory, such as SO10, it turns out that you have this hierarchy of scales between the Planck scale, SO10 scale, where SO10 scale would actually create the magnetic monopoles, and another scale that actually create the cosmic strings. And if you have the cosmic strings, which is basically the Abrikosov clocks of the magnetic flux, magnetic fields, like in type 2 superconductors. But if you do also have the magnetic monopoles in addition to these magnetic fluxes, then the string, which is basically the flux tube of magnetic field, can in principle be cut by the virtual pair production of magnetic monopoles. So if you actually have this kind of grand unified theory, the cosmic strings might actually be ultimately unstable. So it turns out that if you have these magnetic monopoles, then the cosmic strings can't really be cut by the virtual pair production of the magnetic monopole by the Schwinger process, which you know to happen in the strong electric fields. And if we have the minimum magnetic flux, it can be cut by the magnetic monopoles. If we have actually the half the flux, which can happen when the Higgs field has B minus charge 2, then it cannot be cut. It can lead to what is called I forgot the name for this. It's a chain of the sort of the necklace topological defects. So in that case, the string network still remains stable, B minus zero charge. Then the strings really do get cut by the production of the magnetic monopoles by basically the exponent by the wave, the ratio of the wave of the and that may be say as small as 10, between 10 to 15 GeV and 10 to 16 GeV or something like that. So if the ratio is less than 10, then this kind of process does happen within the Hubble time scale. And so you have an early cutoff of the string network of the plateau of the scale invariant spectrum, depending on the ratio of these scales. So in principle, you can completely evade the current constraint from the pulsar timing array. And then you can be still in a reasonable signal range for LISA or LIGO in the future, but can evade this limit from pulsar timing array. So this is the kind of signatures you can expect in gravitational wave coming from the seesaw mechanism, where you have actually connection to both the neutrino mass and grand unified theories. So the last 10 minutes, I'd like to also briefly talk about a potential other scenarios of the baryogenesis, which relies on the first sort of phase transition in some kind of the low energy, the phase transition around the TeV energy scale. So idea here is that we have a first sort of phase transition. It can also in principle satisfy the Sakharov conditions. In fact, the standard model was believed to satisfy all of these conditions earlier on. So standard model is now known to violate the baryon number. We have seen that in the discussion of the anomaly and in the first half of my talk. We also know the CP is violated by the Kobayashi-Maskawa phase. And if you do have the first sort of phase transition for the electroweak phase transition, you can also have departure from an equilibrium and therefore satisfying all of these three conditions. And because all of these things are happening at the electroweak scale, maybe this kind of scenario will be experimentally testable. It turns out that this kind of hope had been dashed in the standard model because the amount of phase we have in CP violation, or rather its size and Yarscock invariant, is extremely tiny, not because the phase is small, but rather because the quark masses are very tiny, like up quark and charm quark masses. So it turns out the size of the CP violating phase is suppressed by these quark masses down to the level of 10 to the minus 20th, while we hope to generate the benefit of generating such a asymmetry in a standard model CP violation. On the other hand, first order phase transition of the electroweak phase transition will require much lighter Higgs boson mass. So again, this hope had been dashed. And so the standard model doesn't seem to achieve all of these conditions, unfortunately. And in fact, the 125 GeV Higgs is actually not a first order phase transition, but even no phase transition at all, because it turns out to be the smooth crossover, came out of some kind of surprise to me, but nonetheless, this is a fact. And therefore, we don't expect the first order phase transition in order to achieve this out of equilibrium condition as suggested by Sakharov. But at the same time, there have been scenarios suggested by Cohen, Kaplan, Nelson by going beyond the standard model, namely the two Higgs doublet model, which can achieve the first order phase transition. And if you do have first order phase transition, you have the coexistence of bubbles of the broken phase and unbroken phase. And as the universe forms the nucleation of the broken phases, which is surrounded by the bubble that would expand, would eventually coalesce with the other bubbles and eventually cover the entire universe, as we seem to have in the universe today. And the particles in the unbroken phase get scattered by this expanding bubble walls, such as the top quark, which has the order Morikawa coupling. And top quark, of course, carrying the baryon number. And in the unbroken phase, the left-handed and right-handed top quark would behave as different particle species. And when the top quarks get bounced around by this reflection from the expanding bubble walls, then reflection coefficient can pick up a CP violation to create a symmetry between the left-handed and right-handed top quarks. And at this point, the baryon number is still unbroken, but you can have the asymmetry between left and right-handed top quarks. But the point here is, again, due to the electroweak spectrum process, the left-handed top quark asymmetry can be partially transferred to the lepton asymmetry. So you lose part of the asymmetry in left-handed top quarks. So the left-handed and right-handed top quarks do not balance in baryon asymmetries anymore, and therefore the loss of the asymmetry in left-handed top quark will lead to actually a finite baryon asymmetry. So that's the way you can generate the baryon asymmetry of the universe, and that is what is usually called the electroweak baryogenesis. But now, after much more careful analysis, which I learned from Gerald and Servan, that you need to actually have a varying baryon number at the CP violating phase within the bubble wall to generate enough to the symmetry. So the concentration in Higgs sector itself. But once you require that, you typically expect to generate a larger violation Higgs sector from this bar Z diagram. Now that there is a stringent experimental constraint from Acme collaboration, while any CP violating phase of order 1 in Higgs sector is expected to generate a large electric dipole moment, which really exceeds the experimental bound by some 7 orders of magnitude. Even if you imagine that 100% efficiency in converting this EDM to the CP violation, you still exceed the experimental limit by some the 4 orders of magnitude. So it seems more and more likely that CP violation should not be generated in the Higgs sector, and therefore the electroweak phase transition is not the source of the baryon asymmetry of the universe. So one simple possibility then is try to do this actually in the dark sector. Just imagine that you have a copy of the SU3 cos S3 cos U1 in a dark sector, similar to the standard model. Just assume that this SU3 cos U1 breaking happens dark sector, a slightly higher energy scale with 2 Higgs doublets, and with CP violation, which is not subject to the EDM constraint, and therefore can lead to both CP violation and the first order phase transition. Then this phase transition can generate both the lepton and baryon asymmetry from the phase transition as envisioned originally by Kaplan, Cohen, and Nelson. And if you actually do have heavy leptons in this sector, which is connected to the standard model by a neutrino portal, then generated lepton asymmetry can be transferred to lepton asymmetry in the standard model. And this lepton asymmetry can further then transfer to baryon asymmetry from the anomaly in the standard model. So that's how you can generate the baryon asymmetry in the standard model. But it is only the lepton number that can be transferred to the standard model from the neutrino portal, and baryon asymmetry still remains in the dark sector, which can actually confine into the baryons in the dark sector by the light up and down quarks. So all the baryon asymmetry remaining in the dark sector gets then contained in a dark neutron or dark proton. And depending on the mass spectrum of these dark hadrons in the dark sector, and this entropy in the QCD can eventually be converted to all the dark pions, and dark pions can decay into dark photons, which further mixes back into the standard model due to mixing, kinetic mixing, and eventually decay into electron positron pairs. So all the entropy then can be successfully dumped back in the standard model. All that remains in the dark sector would be these dark baryons. So the process would basically looks like this. And the lepton asymmetry in dark sector gets converted to lepton asymmetry in the standard model, which further gets transferred to the baryons in the dark sector. And eventually all the lepton asymmetry gets decayed into the lepton asymmetry in the standard model, when baryon symmetry is fixed after the phase transition in a standard model site. And this dark baryon asymmetry gets contained in either dark baryons in the form of dark neutrons or dark protons. So this then becomes a asymmetric dark matter. And at the same time of producing such a asymmetric dark matter, these dark baryons can also have the self-interaction at some level because they got a finite size, which may be actually interesting for the purpose of explaining this velocity-dependent cross-section, which might actually reconcile the lack of cusps in the dwarf galaxies compared to what you typically expect in an n-body simulation of the galaxy formation. And this kind of idea has a long history, going back to all of these famous papers. But what we pointed out is that neutrino portal is really a simple way of connecting these two sectors. I don't go into all these constraints in detail, but the idea is that the enhanced data of the Z factory in the future can look for this exotic decay of the Z boson into this neutrino portal, which would further decay into energetic jets or the lepton emitting energies. And also, now that we have discovered the Higgs boson, you can study them in detail at the future Higgs factories, such as IOC, and then you can hope to see exotic Higgs decay, where Higgs first decays into dark sector, which further decays back into the standard model into missing energy and jets and leptons and in collimated jets, for instance, which can probe this kind of physics 3 to 4 orders of magnitude better and than high luminosity LHC. So if the dark baryons are indeed the dark matter, at the same time of explaining this dark, the baryon asymmetry of the universe, you would predict these dark baryons to be somewhere around 1 GeV mass. And for the QCD phase transition in a dark sector to dump all the energy back into the standard model, you need to have the dark photon, which is lighter than the energy scale. So you can actually have a variety of signature in the future beam dump experiment, fixed target experiments, supernova searches, and also in the direct detection experiment, even though all the action is on the dark side, in addition to this exotic Z decay and exotic Higgs decay. So it turns out that there is actually a wealth of experimental scenarios you can probe this kind of scenario. In addition, you can also have the inverse scenario, where the asymmetry is produced in a standard model. Expected mass of the dark baryons turns out to be somewhere actually close to 60 G area of the parameter space allowed now for the dark photon. And again, you have to expect the second direct detection experiments. Interesting enough, you can even look for the dark neutron in dark direct detection experiments, because the dark QCD can in principle have order 1 vacuum angle. that will lead to large electric dipole moment of the dark neutron, which can then probe by direct detection experiments to the kinetic mixing between photon and dark photon. But now back to the theme of this workshop. You can expect to see, again, gravitational wave signature from this kind of the first order phase transition. If it in a standard model sector, that would be in this frequency range, probed by LISA and BBO, as everybody knows. If the dark phase transition is slightly higher energy scale, you might cut into the LIGO range. So that's a gravitational wave signature which you can indeed look for. And if the energy scale is actually lower, like in the last scenario I mentioned, that the dark phase transition happens below the electroweak scale, then you can also expect to see some kind of signature in actually the galactic archaeology experiments, such as Gaia and Theia, where you can see some coherent motion of the stars, which have nothing to do with each other in the kinetic dynamics of the galaxy. But if you see the coherent motion apparently of the stars at a different depth, and that can be interpreted as a gravitational wave coming through a galactic scale, and therefore you can actually probe such a gravitational wave signal at very low frequencies that will be relevant for the probe of the QCD phase transition at very low energy scale. So that way we can connect the baryon asymmetry of the universe to the neutrino mass, and also in principle the inflation in the dark matter of the universe, in a way that this can be probed together in a gravitational wave signature. And so that's where this ties into the theme of this workshop. And so there are actually many signatures we can look forward to in connection to the idea of the baryon asymmetry probed in the future gravitational wave signature, as well as many kinds of other experiments. So there are actually many things to look forward to. Okay, let me finish now, and thank you for your attention. Hello?
Thank you very much, Hitoshi. Now it's time for questions. Before we start, let me just remind everyone to, apart from asking the questions live, also write the questions in the chat so we can go back to them in the discussion session, because maybe there are quite a few. So after saying this, are there questions for Hitoshi's talk? I presume they just have to unmute themselves and speak.
Okay, go ahead. I'm ready for questions.
Maybe I can just ask one.
Okay, Anish.
Just a small curiosity. So you talked about this hybrid in inflation, where you have two fields. One field is basically getting trapped, and it's affecting like an opening up on waterfall direction. So I guess you could also design some kind of false vacuum inflation as well, and get the same effect. So where the inflation actually happens in the false vacuum, but it does not end via slow roll violation, but instead it ends via the tunneling, and then you.
Well, so it has been studied many times before. The tunneling is actually rather inefficient. So you tend to end up with a universe which keeps inflating forever, or actually finishes inflation too quickly, not to achieving the required 50 or 6 out of the E-folding. So that is probably unlikely. But I have to say that Kai, speaking after me, will probably say more about that.
I see. No, so just a point here. So some people have also studied. So the scenario you're mentioning is assuming Einstein gravity. So if you introduce scalar tensor gravity, for example, like the Higgs inflation, if you include a non-nominal coupling gravity, you can actually stop the universe. Like the false vacuum can really work. But I really don't know for what kind of parameters it works, but probably you can mimic the hybrid inflation kind of scenario and get the gravitational wave signals that
yeah, but for the Higgs inflation, it doesn't lead to the cosmic string network. So it's somewhat irrelevant for the purpose I talked about today.
Yeah.
But that's an interesting question independently from that.
Thank you. Yeah, I think we have one more question.
Salvatore Vitale is raising his hand.
Yeah, hi.
Hi.
So I have a question on which may be on the negative side. So toward the end, you have the slide with the the omega spectrum and some of the ground and space and pulsar gravitational wave detectors. Now, I assume that the line of the signal depends on a lot on the theory parameters. So rather than a line, it should have been, a band or something. So I guess my question is, can you say quickly what you can learn from a non-detection? So suppose, Einstein telescope and the Cosmic Explorer and LISA run and they don't see anything. What interesting properties of the theory can you constrain away?
Yeah, that's actually a more difficult question. So, if you see something, you win. And if you don't see something, then it's actually always subject to interpretations. So if you believe that the baryogenesis has to lead to cosmic strings, then of course you can exclude that. But as I said, honestly, that it doesn't necessarily lead to the conclusion. So it's actually quite likely, but it's not a necessity. So that actually brings in some ambiguity in interpretation. On the other hand, if you do see something, then you learn a great deal, because the scale invariant spectrum, if you can really map out the entire frequency range, it really points to some kind of topological the defect network, which is self-similar. And so it becomes very likely that it has to do with the cosmic strings. Then it has to do with some kind of the homotopy group of the U1 or pi1 of some sort. And then eventually you can try to connect it in the context of quantum unified theories if it actually gets cut by the monopole pair production. So you run a great deal. So non-observation is always subject to interpretation. But if you do see something, then you really do learn a great deal. And the story can become pretty convincing at the end of the day, I believe. So that's why I'm excited about that.
Thank you.
Just to add, I guess, to that, if you don't see something and you rule out all those groups, you will all, in principle, if leptogenesis is right, you would also learn a lot about the embedding, in the sense of you would discard a lot of groups and you end up with, okay, the gut theory that is giving me that has to break in this and that pattern.
I agree. Yes, I agree with you that you still do learn something, but it's not as striking as coming up with the experimental signature. That makes an archaeological evidence for leptogenesis. So I'm just trying to be very honest and fair about that.
I have one quick question regarding the other scenario you discussed, the asymmetric one, which I guess you can fold into. So first, you were putting a specific example, which is this neutrino portal.
Right.
I didn't get, but I believe that there is like a minimum strength of that portal for which this scenario will work. I mean, you need some efficient communication, whatever.
That's right.
Efficient.
Right.
What is the ballpark of that?
Yeah, so that's a good question too. And the answer, unfortunately, is kind of similar to cosmic string, namely that if you require the efficient communication between two sectors, it would still allow for rather very small coupling, because it happens when the expansion universe is already pretty slow. So the future experiments, such as the Higgs factory or Z factory, does not cover the entire parameter space. Again, if you win, if you see something, but it is subject to interpretation if you don't. So that is unfortunate, but that's true.
Okay. Okay. We have one question by Jose Juan.
Hi, Jose.
Hey. So I have a question. Since you have a very detailed particle physics model of the strings, can you tell if you have bound states on these strings, meaning if any of these models can lead to superconducting strings?
So in this case, they are not superconducting. So unlike the axion, because the gauge symmetry is not anomalous.
But but for example, all the other particle content that you have, all the fermions and all this, they don't lead to any bound states on those strings?
So they can be the zero modes, right. But they don't, for example, in the case of the right-hand neutrino, it doesn't carry electric charge. So it's not the superconducting string in a usual way.
Sorry. I guess I abuse the term superconducting here. What I mean is that if you have bound states, which can be massless inside, like zero modes,
right?
This can lead to effects on the strings themselves, because not because they are superconducting, which would be even more striking effects, but they could lead to mechanical effects. If you have a current even if it is neutral,
Mhm.
it can change the tension of the string, and therefore it can change the oscillation of the loops. So it is very important to know if these bounded states exist in your model or not.
I see. You know that. So certainly there is a zero mode for the right-hand neutrino, but it's sort of the Dirac so that it can dissipate. So you should tell me if that still affects the dynamics of the strings, even when they can dissipate because of the annihilation on the string.
So what is the dissipation? If it is a zero mode, it's supposed to be
So
a
if it's like the axion string where the symmetry is anomalous, then the fermi or massless fermi on the string is chiral, and therefore it doesn't dissipate quickly. But if you don't have a
Right.
non-anomalous symmetry, then the left movers, the right movers can annihilate, so that the zero modes would sort of disappear into the bulk.
Right,
So
that-
I'm asking you if the mechanical sort of the behavior of the strings can be affected even in that situation.
I think it could. I mean, but
I
it's
see.
a complicated question
Ah.
because now you have to know what is the end result. So if you have
Okay.
a loop at the end, the loop is going to have some right movers and left movers, and as you
Mhm.
said, they are going to annihilate. But
Mhm.
it's very unlikely that they would have exactly the same content on one direction and the other. And at the end, you may have some sort of net current at the end once
So what
everything is ejected.
So what produces this left-to-right asymmetry on the string?
Well, just because you chop particles, you don't have to chop them in the same way, this way and this way, right? I mean, you have both modes, but the number of particles that you trap doesn't have to be exactly the same.
But isn't that sort of the one over square root n suppressed?
Yes, but then the loop shrinks. And if this leftover current is enough to prevent the loop from disappearing,
Or like
This becomes-
photons?
that's right. This becomes a very
I see. I see.
problem for the model.
Ah, okay.
In your case, you have another mechanism which at the end makes them decay. But what I'm saying is that, I mean, normally when you do phenomenology of the strings, in some sense you make up your model. So you say, well, I'm going to consider the strings and they are not, they don't have any zero modes. But in your case, you don't have this luxury because you're telling me exactly what is the particle physics model. So you should be able to at least estimate if this effect is important or not.
Okay, so then I should study this. So I looked at the photons in the axion strings, and
Mhm.
it seems pretty likely that they would actually disappear. So I hadn't actually thought back at the gauge string in that context, and so I have to think about that. Thank you for the question.
So I believe we don't have any more live questions. So thanks a lot again, Hitoshi, and let's move to the next talk by Kai Smits.
Okay, thank you for your attention.
Thanks a lot. So Kai, whenever you're ready.
Right, can you see my slides?
Yes, we hear you loud and clear and we see your slides.
Perfect. Okay, so then let's get going. So thank you very much for the introduction, and also thanks again for the kind invitation to this workshop. It looks like you've really put together a fantastic program for this week, and I'm really looking forward to all of the days and all the contributions that we'll have. Okay, so I think with what I'm going to talk about now, I will also perfectly tie in into what Hitoshi just told us about, at least the first part of your talk, Hitoshi, because now I will talk a bit more about in detail about gravitational waves from metastable cosmic strings in the context of grand unification. And most of what I'm going to say during this talk will be based on this paper here, which appeared on the arXiv just today. This paper is in collaboration with Wilfried Buchmüller from DESY and Valerie Domke at CERN. But the entire story goes back even a bit further. So we had a paper on metastable cosmic strings last year and also the year before, and Hitoshi was also involved in that. And actually, we've already seen a couple of plots from this very first paper here in Hitoshi's talk. Okay, so I think for this expert audience here at this workshop, it's actually not necessary to really introduce cosmic strings and gravitational waves from cosmic strings, especially after Hitoshi's talk. But still, for completeness and maybe also for everybody who's going to watch the talk afterwards, the recording on YouTube, let me just summarize some of the basics. of cosmic strings. So they are topological defects that can form after spontaneously breaking some U1 symmetry in the early universe. And as Hitoshi has told us already, these strings begin to organize themselves in a network that consists of long strings, typically on super horizon scales, and shorter closed loops, which are chopped off from these long strings in intercommutation events. And that entire network reaches a scaling regime. It enters this stage of self-similar evolution, where, for instance, the fractional energy density in the network remains a constant as a function of time. Okay, two important parameters to describe the evolution of such a network, at least at the lowest level, would be the cosmic string tension. So this is actually mu, the energy per unit length, and G is Newton's constant, so that G times mu is a dimensionless parameter. Another important parameter is alpha. That characterizes the initial size of these cosmic string loops at the time when they form in units of the Hubble horizon at that time. So alpha is again a dimensionless quantity. So I guess as most of you or all of you know, these cosmic strings, they can radiate off gravitational waves, and there are different mechanisms for that. So the loops themselves, they can oscillate in different harmonic excitation states, and that can lead to the emission of gravitational waves. But then you can also have more localized features on these cosmic string loops, namely cusps and kinks, and they lead to a directed emission of gravitational wave bursts. And then if you sum up, or if you sum over all these contributions, the bursts and then the gravitational waves from oscillations, you get a stochastic background signal of gravitational waves from the entire network. Also, a word of caution here at the very beginning. In everything that's going to follow, I will neglect the energy loss from the network via particle emission of closed loops. I know there, I mean, also many of you know, I guess, there's an ongoing debate on this in the literature. And for now, I would just like to refer you to these papers here in the literature. Okay, one more word on gravitational waves from stable cosmic strings, basically just standard ordinary Nambu-Goto strings, in relation to the recently reported signal by the Nanograph pulsar timing collaboration here in the gravitational wave spectrum at nanohertz frequencies. It's not quite clear yet that Nanograph has really seen gravitational waves, and there might also be well-motivated astrophysical interpretations of that signal. And then we will just find out in the coming years what the true origin of that signal is. But at least in these two papers here, right after the Nanograph results had been announced, it was shown that cosmic strings, stable Nambu-Goto strings, are in principle a valid explanation and interpretation of that Nanograph signal. So you can reproduce the right amplitude here at the nanohertz frequency range. Okay, so if you adopt a standard assumption regarding the size of these cosmic string loops, you assume a loop size parameter of alpha around 0.1. It turns out that you can explain the Nanograph signal for a tension of around 10 to the minus 11, 10 to the minus 10 or so. That needs to be compared to what you would expect if you produce these cosmic strings at very high energies, maybe in dynamics related to the GUT scale. So say at energies around 10 to the 15 to 10 to the 16 GeV. And in that case, typically you would expect slightly larger values of the cosmic string tension, around 10 to the minus 8 or 7 or so. As has been pointed out here in our paper, you can actually achieve such values of the cosmic string tension if you allow for smaller values of alpha, but then it's an open question whether you can actually achieve such small values alpha in realistic networks. Okay, independent of that, it also turns out that you can take the signal here at low frequencies, you extrapolate this to higher frequencies, and then you realize that this interpretation will not give you a signal that is strong enough to be detected by the second generation ground-based interferometers, such as LIGO, Virgo, and Encagra. Obviously, you will be able to test this interpretation here with these future experiments at missions, but you won't be able to see the signal here with a second generation of ground-based interferometers. So one question is there a possibility to go beyond the scenario? Maybe also consider scenarios of a cosmic string network that are a bit more realistic, that are connected to particle physics at very high energies, where some of these points might change, where you can actually have strings that are produced at very high energy scales and being still consistent with nanograph, and where you can also actually predict a signal within the sensitivity reach of the current ground-based interferometers. All right, so let's, that's why I want to basically directly continue with what Hitoshi taught us during his talk. Here I'm referring to his paper from 2019, where they also showed this figure here, at least in some early version of the paper. And in the conclusion, or the upshot from this, is that you cannot only, or you should not only look at the production of cosmic strings by breaking some U1 symmetry in isolation, but it makes much more sense to take that picture and embed this into a bigger framework. For instance, grand unification, to see how this affects the dynamics of the network and the conclusions for cosmic strings. So for instance, if you take the seesaw mechanism that Hitoshi introduced in his presentation, and you look at UV embeddings of the seesaw mechanism in grand unified theories, then you encounter this, this picture where the dynamics of neutrino mass generation, leptogenesis, cosmic strings, and gravitational waves is completely connected and interrelated. You may also be able to make statements on proton decay. This is something that has been discussed by these authors here. I've seen some of them also in the audience right now. There was a paper last year and then a second paper very recently on the connection between gravitational waves, cosmic strings, and proton decay. Okay, so I want to look at one particular example here in this picture, namely the breaking of the standard model gauge group times U1B minus L down to the standard model gauge group. Yeah, so this is basically this blue arrow. You start from this green box here, and then you follow this blue arrow to break the gauge group down to the standard model. Alternatively, you could also break it down to the standard model times a discrete Z2 symmetry, meta parity at low energies, and then you would find a stable Z2 string. This was also shown in Hitoshi's talk in that table that gave you an overview of all the different topological defects that you can produce here in these scenarios. But if you follow this symmetry breaking pattern here, if there is no preserved meta parity at low energies, then the cosmic strings produced in that process will be meta stable. That means they are unstable against quantum tunneling events on the string that lead to the production of SL10 monopole pairs. Hitoshi also had a very similar picture in his talk. All right, before we continue, just one more important assumption. This entire picture requires that there is this intermediate stage of inflation. It's shown here. So you want to have inflation that dilutes any primordial abundance of monopoles that might be produced here at the first symmetry breaking stage. In the B minus L scenario, if that doesn't happen, this would actually lead to a gas of strings and monopoles after you've broken down the full gauge group. And such a network would not be very long-lived, and you would not have the same phenomenology as in the case of just a meta-stable cosmic string network. All right, so this is another important assumption. There needs to be inflation in between these two symmetry breaking stages. Okay, so how do we describe the production of monopoles along these cosmic strings? The most important quantity maybe is the decay rate per string length. This has been worked out here in these papers. The decay rate itself has mass dimension 2, so it's the number of nucleation events on these strings per unit time and per unit string length, L. And it turns out this quantity is given in terms of basically two parameters. One is mu, the cosmic string tension, and then there is this kappa parameter here up in the exponent that quantifies the exponential suppression of that rate. And then kappa is given by the ratio of the monopole mass, m, the mass of these monopoles here, and the cosmic string tension mu. All right. So if that rate is non-zero, it just tells you that the strings are not topologically stable, but they decay on cosmological time scales. So depending on the parameters that you put here, this might lead to a scenario where this cosmic string network decays, for instance, around the time of meta radiation equality, maybe earlier, maybe much earlier, or maybe even a bit later. But it's certainly possible that it takes some macroscopic amount of time before the network actually decays. So in the following, I will be interested in scenarios where some common dynamics around the gut scale really generates these different mass scales. So I assume there's no large separation of scales between the cosmic string tension and the monopole mass. And in that case, this parameter kappa, square root of kappa, will be some number of order 1 or 10. So we'll see that values around 7 or 8 will be particularly interesting. And in that case, you can really talk about metastable strings, which are first produced, but then also decay after some cosmological time. On the other hand, if you produce these cosmic strings at some intermediate energy scale, much below the gut scale, then mu will be much smaller than the mass of these gut monopoles. Kappa will be very large, and this rate will be strongly and exponentially suppressed. So if the square root of kappa should be much larger than 10, then this network will have a lifetime longer than the age of the universe. And for all practical purposes, you can just treat them as stable cosmic strings. So in this sense, then you would work with these quasi-stable cosmic strings. Okay, so here in this figure, you see I put a color on these monopoles. This is just to indicate that you can distinguish between a couple of different cases, namely monopoles with or without unconfined magnetic flux. Hitoshi also already discussed the case of some unconfined magnetic flux. And in that case, you would actually talk about monopoles and anti-monopoles. And then once these monopoles and anti-monopoles nucleate on the strings, you would assume that the dynamics of the remaining segment is controlled by the dynamics of the monopole and the anti-monopole. They will quickly annihilate and basically emit the entire energy contained in the segment into massless gauge bosons. So in that case, you would not expect to get any contribution to gravitational waves from these string segments. However, in principle, you could also consider the possibility that these monopoles do not carry any unconfined flux. In this case, you produce this segment. There's no real interaction between the monopole, or the would-be anti-monopole, and then the entire remaining energy in the string segment can then only be released via the emission of gravitational waves. In the following, I want to remain agnostic about what actually happens in a realistic scenario. We can just study both cases and then see what would be the contribution from the segments if I include them or if I don't include them. Okay, yeah, I just want to spend one slide on possible scenarios where you can obtain such a network of metastable cosmic strings. I can be brief here because Hitoshi talked about this already in some detail. So one idea would be to really look at the cosmological breaking of B minus L at the end of supersymmetric hybrid inflation. And in this case, you would start with such a superpotential here. T is the inflaton field, S and S bar are the B minus L Higgs fields, or in the terminology of hybrid inflation, these would be the waterfall fields that undergo this waterfall phase transition at the end of inflation. They break B minus L, and that leads to the generation of the cosmic string network. Now we can create right-hand neutrino masses in that scenario if the coupling to the right-hand neutrinos is of this type here. So we need to have this S squared and some high dimensional operator with a UV cutoff scale here. In that case, we can assign a B minus L charge of -1 to this field S, which means that there will be no meta parity preserved at low energies. And this is then exactly what makes the cosmic strings metastable. We studied this scenario in a series of papers, actually independent of metastable cosmic strings, just to show that this leads to a consistent cosmology that gives you inflation, neutrino masses, leptogenesis, and also possibly dark matter. We revisited the scenario in 2019 in collaboration with Hitoshi. And then we identified some viable parameter space where all of the things I just mentioned, they work out. And then you have a prediction for the B minus L breaking scale. So in this case here, you can read it off. It would be between 3 and then 6 times 10 to the 15 GeV. That would give you metastable cosmic strings with a pretty large tension, maybe around 10 to the minus 7. And that value is also close to the gut scale, which means that in this scenario, you would expect a small value of this kappa parameter that parameterizes the cosmic string decay rate. So you would expect to have cosmic strings that decay on some relevant cosmological timescale. Now, if this looks too complicated to you, or if this combines too many ingredients, I can also just mention a very simple and minimal alternative to this model here. This has been studied by Buchmüller earlier this year. So you don't actually have to talk about grand unification. All it needs to generate a network of metastable cosmic strings would be to start from some SU2 cross U1 symmetry. And you want to break this down to U1, but you don't start with some doublets. Instead, you use an SU2 triplet to break this gauge group down to U1 cross U1. That produces SU2 monopoles. Then you have to invoke cosmic inflation to basically solve the monopole problems. You want to dilute, you want to inflate these monopoles away. But then after inflation, you use doublets to break that U2 cross U2 symmetry down to the final U1 symmetry. And in that second symmetry breaking stage, you finally produce cosmic strings, and they're metastable because of the topology of the full gauge group that you've just broken. And then these metastable cosmic strings, they are then unstable against the decay into they're unstable against the nucleation of these SU2 monopoles on the strings. Okay, so this is just a particle physics motivation or background for why it's interesting to think about metastable cosmic strings. Okay, so now in the remaining couple of minutes, I just want to outline the strategy that we use to describe this network and the associated gravitational wave signal. So we expect that at early times, much shorter than the lifetime of the network, everything can still be described by the usual scaling regime. And the question is, when does this scaling regime end, and when does it transition to something else? And then for this, we can consider the number of nucleation events in the cosmic string network and estimate this quantity here for strings that have a length of the order of the horizon. Or we want to know, when do we actually see the first nucleation events inside the Hubble horizon? Now, the Hubble horizon itself is proportional to time. So this gives me a t squared here, which indicates that this quantity becomes of order 1 at this time ts, which is roughly given by 1 over the square root of the decay rate. So this is an important time scale at which we expect the scaling regime to end and to transition into something new, which describes the decay, the collapse of the network. So at early times, we are still in the scaling regime that consists of loops. They emit gravitational waves as usual. But then on these small subhorizon scales, we expect that the decay into shorter segments is still negligible at these early times. We also have long strings in the network. They actually do decay into segments, but they decay on superhorizon scales, such that within a Hubble horizon, everything just looks like in the standard ordinary scaling regime. These long strings, they also chop off closed loops as usual, but the gravitational wave emission from these long strings is still negligible, more or less at these early times. All right, and that transitions now to something else at much later times. So after TS, the end of the scaling regime, the loops, they still emit gravitational waves, but they also decay into segments here on subhorizon scales. That leads to a population of segments from loops, but also the long strings, they decay into shorter segments. And all of these segments now become dynamical. They oscillate inside the horizon. They emit gravitational waves, and they keep decaying into smaller and smaller and smaller segments. And because now these segments have become dynamical and emit gravitational waves themselves, we expect that they're no longer very efficient in producing new loops. Okay, so to describe this more formally, you have to look at kinetic equations for the number densities of loops with a little circle here above and segments with a little tilde above. And these kinetic equations have this general form here. The most important term is maybe the source term here on the right-hand side. For loops from long strings, it's just given by the standard loop production function at early times. Then we say during the decay regime, we don't produce any more new loops, so we just put the source term to 0. We can produce these segments from loops at late times. That's just proportional to the decay probability here on the loops times the loop number density. And we can produce, and this term is active all the time, basically, short loops, or shorter segments from longer segments. And this is given by an integral expression because we have to integrate over the entire available population of segments that can split into shorter segments. We also have a second term here that describes the time evolution of the string length. Long strings during scaling have such a function u here. The first term describes Hubble stretching, and the second term describes energy loss into loops. And then whenever loops and segments radiate off gravitational waves, the time dependence of the length is just given by these expressions here with a minus sign. So this accounts for the energy loss via the emission of gravitational waves. Okay, so this is the formalism. And now the challenge is to set up this set of partial integral differential equations in both the scaling regime and the decay regime. You solve these equations and you match the solutions at this transition time. And in our paper, we have to also pay attention to the background evolution. So we do all of this in a radiation-dominated background and a matter-dominated background. So because time is short, I can just show to you one result as an example. So here's the loop number density during the decay regime in the radiation era. And for the experts in the audience, you will notice that this is already very similar to the expression in the BOS model, but there is an important modification. Now we have some exponential suppression term here that describes the decay of these loops during the radiation era in the decay regime. So we have this exponential suppression that becomes efficient whenever one of these two conditions here is satisfied. So whenever the first term is large or the second term is large, then this exponential factor will kick in and exponentially suppress the loop number density. And it's quite intuitive to see where this comes from. So this exponential factor here is just given by this integral. Inside the square brackets, you see the time dependent of a string loop as it emits off gravitational waves, and you perform the integral. So that gives you basically the decay rate times some average loop length within a certain time interval times the time interval itself. So this is basically exactly what you see here up in the exponent. And with this modification of the number density, we now have a time resolved picture of loop decay independent of the loop length and the time coordinate t. And this is just one result. And then if you look at the paper, you can see similar results for all the other number densities. So loops doing radiation domination, matter domination in the scaling regime, after the scaling regime, number density for segments from other segments, segments from loops, and so on and so forth. You can look at all these permutations. And it can become quite complicated in some of the cases. For instance, the number density of segments from loops is described by an integral differential equation that can only be solved by some infinite series that needs to be evaluated order by order. But you can find the details in the paper. So I have 2 more slides and then I'm done. So these number densities are our main new results, and we can just use them to calculate the gravitational wave spectrum in the standard way. And here I show to you some of the most important results. So here are some example spectra from metastable cosmic strings as a function of g mu, the tension, and the kappa parameter. We find that the contribution to the spectrum from loops is always dominant. That's interesting because there has been this important pioneering paper here more than 10 years ago, and they just looked only at the segments, but now we find that the loops are actually more important. And we also improve on our own analysis from 2 years ago. So in the paper that Hitoshi showed, where we didn't have that time resolved picture, we still found a power law index of 3/2 here at low frequencies. But now, because we can time resolve the entire decay process, we actually find a power law index of 2 at low frequencies. And now you can see that we can use that exponential suppression to suppress the spectrum at low frequencies, which in turn allows us to go to larger values of G times mu. And now we can explain the nanograph signal for much larger values of G times mu, larger string tensions. Okay, so this is my last slide. We can also look at the observational prospects for experiments at higher frequencies. Here on the left-hand side, you see our parameter space as a function of G mu and kappa. We can explain nanograph in quite a large region, but then if you extrapolate the spectrum all the way up to high frequencies, you see that LIGO, for instance, starts probing into that parameter space already, and it will even continue probing this parameter space in the future. We can also use our spectra to correlate two important observables for the future, namely the tilt at PTA frequencies and the amplitude at interferometer frequencies. And then you see that there's this non-trivial correlation among the two if you want to explain nanograph. LIGO will probe further and further into this parameter space. And then if in the future, one of these points here should be confirmed or the experiments should narrow in onto that point, it would provide interesting evidence for metastable cosmic strings. And I should also say LISA eventually will probe the entire viable parameter space. So my time is up. Let me just briefly conclude. I talked about metastable cosmic strings. I presented some predictions for future PTA and interferometer experiments. Next steps would be to explore other directions in parameter space. Obviously, it would be awesome if such a network could be numerically simulated on the computer, because all we've done was to do some analytical estimates, and then we set up our own scheme to describe the dynamics. But if this could be cross-checked on the computer, this would be fantastic. And then you can also think about other observables, for instance, consequences of this monopole, anti-monopole annihilation, or for instance, consequences for CMB spectral distortions. But that's it for this talk. So thank you very much for your attention.
Thanks a lot, Kai. Thank you very much. Now, yeah, it's time for questions. Please go ahead. I also remind you that you can also write them on the chat for the discussion later.
Do we have some questions in the chat? No, this was somebody else. This was Anish. Yeah, okay.
At least 2 questions live.
Yes, please.
Hi, thank you. Thanks for the wonderful talk. I have a related question to PTA detection. So I heard this cosmic string could produce that frequency dependence pretty well, and but nanograph on itself does not give a strong evidence for the discovery of stochastic gravitational wave, because angular dependence, which is the so-called Helens-Downs curve, is not matching very well. So I was wondering, how would this type of cosmic strings generated gravitational wave affected this part of the detection? I understand like this is the energy density part. So how would this cosmic string generated gravitational wave affect the angular dependence part?
Yeah, so thank you very much for this question. I think you're raising a couple of interesting points. So I tried to say this very briefly. At the present stage, the signal reported by the nanograph collaboration is not conclusive yet, in the sense that we can claim the detection of a stochastic gravitational wave background. They clearly see a signal, but it needs to be confirmed whether this is really gravitational waves or maybe some other kind of systematic effect. And as you correctly pointed out, basically the hallmark signature of gravitational waves in a PTA experiment would be this Helens-Downs curve, which quantifies the angular correlations among the different pulsing signals from different pulses. I would not say that the most recent nanograph data is in bad shape or it doesn't do a good job at explaining or at reproducing this Helens-Downs curve. The point simply is that the error bars are still too large. So at the present stage, you just cannot make this statement at the required amount of statistical significance, but the data is in no way in any tension with the assumption of really Hellings and Downs correlations. I don't have the plot here, but you can look at the nanograph paper. There you see the reconstructed angular correlations, and they nicely cluster around the theoretical prediction from the Hellings and Downs curve. The point simply is that the error bars are still too large. So I think I actually look at this in kind of a positive way. So it's still perfectly consistent. We just have to wait for a bit longer. And in the coming years, with more data, more PTAs, and in larger data sets, these error bars will become much, much smaller. And then we'll be able to have more conclusive evidence for these angular correlations. I should also say the Nanograph collaboration has put out a paper in last October where they do a projection into the future, and they show what will happen with 15 years of data, 17 years of data, 20 years of data. And then from this, they can conclude that with a slightly larger data set, so maybe 15 to 20 years of PTA data, this will be enough to really pin down these Hellings and Downs correlations. And then if the signal is really of a gravitational wave origin, then all the sources that have been proposed so far, these supermassive black hole binaries, phase transitions, but also cosmic strings, because they are all one form of a stochastic gravitational wave background, they will also lead to that characteristic correlation pattern. So that's one point. And then besides that, you will need to have a better resolution of the spectral tilt. Basically, like in this plot here on the right-hand side, you have to measure the amplitude, but also the tilt. And that may help to pin down the real origin and the source of the signal.
I see. Thank you so much.
Mark?
I guess you can wait for Lisa.
Yeah, of course.
We have one question by Mark also.
Yeah,
Mark,
hi, thanks. Thanks for the talk. There's lots of interesting stuff in there. Yeah, so you mentioned near the beginning that you're assuming the standard Nambu-Goto scenario, which is kind of understandable in a conference devoted to gravitational waves.
Right.
But I was just wondering whether you had thought about the consequences of this other scenario, which is sort of favored by the numerical simulations, which you kind of talk about, that basically strings collapse into massive particles pretty much as soon as they can. What would be in that scenario, what would be the observational implications?
Right, yeah. So I mean, I only had 20 minutes, so I didn't really have much time to squeeze anything on this discussion here in this short talk. I think the best I could do was to put this assumption here right at the very beginning. And please note that I also cite your very recent paper on this. So
I did note, thank you.
Yeah, we're certainly aware of this discussion. I'm not sure whether I'm really qualified to say anything meaningful on how these open questions could be resolved in the future. My impression is that if you have very efficient particle emission from closed loops, then that will certainly give you a strong suppression in the gravitational wave spectrum. You could still hope that the long strings in the network, whenever they reorganize themselves in the scaling regime on Hubble scale length scales, that they would give rise to a contribution in gravitational waves. I mean, one of our very first papers here on gravitational waves from cosmic B-L strings also has an estimate of that contribution to the gravitational wave spectrum. It would be strongly suppressed compared to the Nambu-Goto case. And I think in that case, it would be really hard to fit it to the nanograph signal. It might still be there, and then you would have to hope for more futuristic experiments like BBO. They would have a chance to see such a strongly suppressed signal. But on the other hand, I mean, I think in more general terms, I think an open question also is if you do have that efficient particle emission from the cosmic from the string loops, the question is, can you actually retain any, even if it's only a slight amount of cosmic string loops, or do they disappear completely? I mean, if they disappear completely, then the entire associated gravitational wave signal would be gone. If you can keep a certain fraction, maybe just a very small number, maybe just 1 out of 1,000 or 1 out of 10,000, it could be that at late times, that surviving string loop might still give a contribution to gravitational waves.
Yes, thanks very much.
Okay. So we are a bit late on time, so let's. Thanks a lot, Kai, again.
Yep,
I
thank you
guess
very
we'll
much.
have more discussion in the discussion session. So the next speaker is Lara Souza. Lara, are you there? Yes.
Yes. Can you see the slides?
You can see the slides and hear you properly, so please,
Okay.
the floor is yours.
Okay. First of all, I'd like to thank the organizers for the invitation. And since the theme of this conference is physics beyond the standard model, I decided to bring this work that I've done in collaboration with Pedro Avelino about the gravitational wave signatures of cosmic superstrings. Because first, it is way beyond the standard model, and also because although this paper is already 5 years old, I believe it is still relevant, especially given the recent possible detection by nanograms. So string theory basically describes particles as 1+1 extended object, as 1+1 dimensional extended objects. And when this was proposed, of course, people already knew 1+1 dimensional extended objects, cosmic strings. And so people started asking straight away whether these were related and whether superstrings could actually behave as cosmic strings. And the answer straight away was no. Witten already in 1985 said that they couldn't because, first of all, superstrings are created around the Planck scale, so their tension would be too high and they would spoil observations. And they also would be, macroscopic superstrings would be unstable to fragmentation. And since they would happen before inflation in general, actually these superstrings would be diluted and we should not expect them to play a significant cosmological role. But more recently, in the early 2000s, people realized that this is no longer the case in the brane world realization of string theory. So in this case, we are living in a 3-dimensional D-brane embedded in a 9+1 dimensional universe. And inflation could be simply realized in such a scenario if we have an additional pair of branes or a pair of brane anti-brane. And this brane, if they collide, so as they are moving towards each other, they would generate, their interactions would drive a phase of accelerated expansion, and this inflationary stage will be naturally brought to an end as these pair of branes collides. And when this happens, a part of the energy of the colliding branes will be trapped in the formation of lower dimensionality branes, and these would be in general one dimension. There's several realizations of brane inflation, and in several of those, there is the prediction that there will be the copious production of stable fundamental strings, or F strings, I'll call them that from now on, and one-dimensional D-branes are D strings, and this would be actually stable and could be macroscopic, so this solves two of the problems we had initially. There's also the problem of the tension being too high, but this is also solved if we notice that in this universe with extra dimensions, basically the extra dimensions are compactified. That's why we don't see them. But there could be regions such as this throat that I have here in this figure, where there's high curvature. So that these are very, very worked regions. And if the brane collision happens in this throat, the strings created would appear, although they have a high tension, they will appear to have, to us as 3-dimensional observers in the brain, they would appear to have a lower tension. So basically, these brane inflationary scenarios can indeed provide a mechanism to create cosmic superstrings that can grow to macroscopic sizes and basically play a cosmological role that is similar to cosmic strings. This is what I refer to as cosmic superstrings. And of course, this got people interested because this provides a window into string theory, and already a lot of people worked on cosmic strings, so they're eager to extend their work towards this. And gravitational waves are particularly interesting in this case. So let me go back to ordinary strings to discuss what happens in string interactions, because this is very important to the creation of loops and the emission of gravitational wave background. So when two strings collide, and here I have a representation of the strings. I use two colors for visualization purposes only. These strings are identical, and so when they collide, they basically break off, and the end of a string attaches to the end of another like this. So basically, we end up with a situation in which we have two strings which have exactly the same length as before, so the same energy, but they have curvature. And for ordinary strings, this happens every single time strings collide. So we say that the intercommuting probability is equal to 1. Well, this, as a result of this intercommutation processes in situations such as these, where we have two curved strings colliding or a string self-intersecting, we may have the formation of closed loops. And these loops basically detach from the network and they start to emit gravitational waves. And as they do, they lose energy and they shrink until they eventually disappear. So this gives rise to a transient burst of gravitational waves. And since interactions between strings and collisions are very frequent, we expect that there is a large number of strings at any point in the evolution of a network. And so there may be, we expect there are a lot of loops emitting gravitational waves simultaneously in different directions. And this gives rise to a stochastic background. Here I have the figure of a typical stochastic background. Basically, it's always like this. It has a flat portion in the radiation era, but actually this may not be exactly flat. There may be other hints of physics beyond the standard model on this flat part, but I'm not going to get into this. And there's also a peak in the low frequency region that is generated by loops created that are decaying in the matter era. And although this is basically the general shape of the spectrum, the amplitude, the location of the peak, its broadness, its height, this all depends on a number of details of the cosmic string network. So on the number of loops that exist and all of their lengths. So to compute this, we need to know a few things. So we need to know how much energy is going into loops. And this is basically knowing how the energy density of the network evolves, what is the length of the loops that are created, and what is their emission spectrum. And so in this paper, what I wanted to do is to compute the stochastic background generated by cosmic superstrings. And this basically reduces to answering the questions that I've shown you before, or basically this question reduces to what we know about string loops. And one thing that is being known for a while is that intercommutation is different. So as before, when two superstrings of the same type collide, there's a probability P that an intercommutation will occur. So we have the same thing as before, but there's a 1 minus P probability that there will be no interaction at all. So they may simply pass through each other without interaction. And this is merely a result of their quantum nature. And because of this, and actually for ordinary strings, the probability is 1, the probability of intercommutation, but for superstrings, this can be significantly smaller than 1. And so because of this, basically, when a collision occurs, it is less likely than that an interaction will occur. So an intercommutation will occur. So it's also less likely that a loop will form in the situations that I mentioned. So the energy that goes into loops that I represent here with a parameter, with this parameter C, actually decreases with decreasing P, and this means that we have less energy going into loops. This exponent gamma here is a matter of debate, but we can still discuss this qualitatively, so I'm not going to get into the details of this. But what this means actually is that the characteristic length of the network is going to also decrease with decreasing intercommuting probability. So the strings would be shorter and closer together there. So we'll have more strings crammed into our comoving volume. So this means that the networks are denser. And although it is less likely that in a collision, a loop is going to form, we have so much more strings in our comoving volume that the amplitude of the stochastic gravitational wave background actually will increase with decreasing P. And so when people try to estimate the spectrum, what they usually do is just to take the spectrum of ordinary strings and use this relation basically to scale it and to infer what is the spectrum of superstrings. But there's a few other things few other properties of cosmic superstrings that are relevant, and I wanted to actually take those into consideration too. So there's, as I mentioned, there are 2 types of strings here. Now the different colors are different strings, and we have F strings and D strings, and these strings have a higher tension in general, which is controlled by this GS parameter here. And these two types of strings do not commute. So basically when they collide, they bind together and form a new type of string. And so when this happens, F strings and D strings lose a part of their length into the formation of what we call a one string. So it's a bound state of the two strings. And this new string has a heavier tension. And this 1-1 string can also collide with a 1-0 string and a 0-1 string, and this would give rise to even heavier string types. And this can happen recursively in the evolution of the network. So we may actually have a hierarchy of string tensions with strings with different string populations with increasing tension. And as a result, we actually may have several populations of loops. So a population of D string loops, a population of F string loops, a population of 1-1 string loops, etc. So what I want to do in this paper is to see what is the contribution from all of these loops. And to do this, of course, one thing that one needs is to know how much energy goes into loops. But luckily, there was already some analytical model that gives us the evolution of the energy density of cosmic string network. So this was developed in a series of papers that I list here. And basically this model takes into account the kinematic constraints on the formation of junctions, or because these do not happen in all of the collisions, and also the dynamical impact of the junctions on the evolution of the network. So basically, from this, we can, what I use this model to extract the number, how the energy density of the different types of strings evolve throughout cosmological time. And from that, I can infer how much energy is going into the formation of loops as a function of time. There's also simulations of field theory analogs to cosmic superstring. These are non-abelian strings. And actually, these two were compared, and they are in good agreement. And in both cases, what we see is that in general, as the tension increases, the energy density of the string decreases. So in general, we only need to take into consideration the three lightest type of strings, because even heavier types will just have a negligible contribution to the energy density. So what I did is precisely this: use this analytical model to see how much energy goes into loops as a function of time for the three lightest type of strings. And of course, this is not sufficient to compute the spectrum. We also need to know a bit more about loops. And this is what actually we don't know a lot about. So the loop distribution function for these superstrings was not measured. However, there's some simulations by Avgustidis and Scheller where they actually mentioned that they see that their loops tend to be smaller than in ordinary strings, and this is because this reduction in the intercommuting probability is more efficient at suppressing the formation of large loops than it is in suppressing the formation of small loops. So we may expect loops to be close to the gravitation back reaction scale. And they also seen that there is a buildup of small scale structure, so these loops are expected to be quite kinky, but we don't know much more than that. And in particular, we don't know the efficiency of gravitational wave emission. So the best we can do is to assume that it's similar to that of ordinary strings. This is, of course, an assumption in what I do, but is also an assumption in the simplified model that I mentioned that people use, that is by taking just the spectrum of ordinary strings and scaling it. But yeah, there's some information missing here. But in any case, we can do a qualitative study of the spectrum to see if it is different from the spectrum of standard strings. And this is what I did. So what I wanted to ask is whether this simplified model that people use, which is basically taking the spectrum of ordinary strings with lower p, will actually give us a good description of the network, or whether we need to include heavier strings. And here I have a plot of the spectrum generated by the lightest string type only. It is represented in red here. And in white, I have the approximated model that people grab. So this is a good fit to one type of string only, but even in this case, we can see there's a slight discrepancy in the amplitude of the spectrum. And this is basically because of the dynamical impact of junctions. In this case, this is tiny, but in other cases, as we shall see, this can be this underestimation can be larger. But now I also wanted to include the contributions of these strings and one-one strings, and here they are in blue and yellow. And as you may see, when we use this simplified approach, we lose information about these other types, and actually the total background may in the low frequency range be significantly different from the approximation that people use. Of course, this is one example, but I scanned throughout different possibilities. I consider, for instance, models with loops with different sizes. With large loops, these are, I think, a tenth of the correlation length. We always have signatures on the low frequency range, and these signatures are as we go from right to left, the tension of these strings increases. So we can see that if the tension of these strings is larger, the signatures are more prominent. But on the right, where the tension of the F and D strings are comparable, what we see is that there's also a significant underestimation of the overall amplitude of the spectrum. So we also lose some information here. This is the case for large loops. This is also the case for loops created at the gravitational back reaction scale. So we always have these signatures on the low frequency range. And in this case, for these strings, they are quite prominent. And it's almost as if we have a very prominent secondary peak in the low frequency range. And even for smaller loops, we always have these signatures in the spectrum, which are qualitatively the same, independently of loop size. So basically, we cannot really neglect the contribution of heavier strings because they may leave distinct signatures. And of course, the question is whether this matters. And of course, I think it matters, otherwise I wouldn't be talking about this. But actually, what the people do when they simplify the model and take ordinary strings with reduced intercommuting probability is that every model that has the same intercommuting probability for F strings is predicted to be exactly the same. So this blue and yellow model, which are significantly different, which have different tensions for these strings, and also which in the yellow model, strings cannot explore a larger, significant portion of the extra dimensions. They are a bit bound to our brain. The simplified model predicts exactly the same for all these models. So basically, if we superimpose this, we see that they are clearly not the same. And if we look at these signatures in the low frequency range, we can actually get some information regarding the underlying superstring theory. And this is why I think this matters. So it is these signatures that allow us to distinguish between ordinary strings and superstrings, and it is also the signatures that will allow us to discriminate between superstring models and get information about the tension of the D strings. But this simplification also has impact on the constraints we derived. In this paper, I derived the constraints that resulted from non-Grab 9-year data. This is just an example, and this is the colored region is the region excluded by nanograph 9-year data if you assume the simplified model. So only take into consideration F strings and do not account for the effect of junctions. If you include the effect of junctions, this region grows a little bit more. We can exclude a bit more. But if we include the heavier strings, the D strings and 1-1 strings, actually we have a secondary exclusion region. And so we can put more stringent constraints on these scenarios. And an interesting thing that this shows us is that actually with pulsar timing array, since they probe the low frequency range, we can actually detect heavier strings without detecting the lightest type of string. So if we don't know how this contribution looks, we may actually misinterpret the signal we get. So basically, yeah, this matters because this is actually where the physics, or at least the physics related to string theory is. And this is my main takeaway and message in this talk, is that we need to include the contributions of various strings if we want to get some information regarding this. However, I wanted to, before finishing, I wanted to say that this is not sufficient because there is a lot we don't know about cosmic superstrings. For instance, as I mentioned, we don't know the gravitational wave emission efficiency, and actually we don't know if there are other decay channels. People suggest, for instance, that they can emit axioms. There's also other aspects of the dynamics that should be clarified, and yeah, I could list a number of things that we need to understand in more detail to be completely confident with this. But what I argue here is that this is at least a step towards the right direction, and that we need to consider this to actually try to discriminate between models. So to sum up, basically, we've been oversimplifying the spectrum of superstrings, and by doing so, we've been losing information, and we actually been getting weaker constraints than we should. These constraints, of course, are safe. They are weaker, so they are safe, but we may be losing some information in the process. So that's all. Thank you.
Thank you very much, Lara. Time for questions. We have to be a bit quick. We have some discussion session later on, since we're running a bit behind. I have a quick question. So if I understood correctly, I'm not really an expert on this matter. I understood that in your case, the name of the game is really in the low frequency part where you want to distinguish models. And then you showed a plot saying, okay, what is the region of parameter space that current PTAs are ruling out, constraining.
Yeah. This is assuming a particular size of loops because we don't know the size of loops. So this is close to the back reaction. So this actually would be weak constraints.
I was lacking or missing, or so since you're talking about being able to discriminate different models, different even string theories with this, is there, do you have some idea of the PTA sensitivity for this discrimination, say in a plot like this? Is this something that...
Well, in that case, we would have to look into the reconstruction of the spectrum. So we would have to inject spectrum to see how well we can reconstruct. But what I wanted to say here is that since models can look quite different in the low frequency range, we need to know these signatures to be able to do this reconstruction and to include these heavier types in our reconstruction of models.
Okay, but you are somehow saying that precisely at least what you're showing here, the feature that has the greater discriminating power falls precisely in the region, in the frequency region where
well, if you lower the tension, everything moves towards the higher frequencies. So for very low fundamental tensions, this can go to Lisa window and etc.
Okay, thanks a lot. Okay, well, any more question, we'll have to go into the discussion session because we are running a bit late. So the last talk of this session is by Jose Juan Blanco Pillado. Jose Juan, are you there? We know you're there. Already asked.
Can you hear us? Hear me?
Do you want to share? Okay. Perfect. So whenever you're ready, we are.
All right. So thank you very much for the invitation. It's a great pleasure to be here. So the title of my talk is Stochastic Gravitational Wave Background from Cosmic Strings. A lot of people have already discussed parts of my talk, which is good, because I will go a little bit faster, which I think everybody would appreciate since the last one. But I will concentrate on topics which are specific about simulations, which we have been doing in the last few years in collaboration with people at Tufts, Ken Olin, Ben Schleyer, Javier Siemens, and also with Jeremy Wachter, that was also a postdoc here in Bilbao. So I will concentrate on things that we can learn from our simulations. So first of all, I want to, since we've been discussing different types of strings, I want to set the stage of what the strings I'm going to be talking about. I'll describe topological strings, topological defects, which means that these strings are going to be infinite. They will not have any end, so you will either have infinite strings or loops. Okay. The problem I have is the formation of a network of strings, and it only has one energy scale, which is this parameter eta, that basically sets everything that we need to know. For example, it sets the tension, which in this case, in these objects, the tension is the same as the energy density, so they are relativistic strings. And the energy per unit length, which is denoted by mu, is basically eta squared. So everything is going to parameterize with this single parameter, and we normally use it as people have been discussing before. We use this dimensionless number parameter, which is G mu, which is the ratio of the string symmetry weighting scale to the Planck scale. So typically this thing is very small if you square. So if you take, for example, for a gratified theory string, this would be 10 to the -6. But if you go down, as this is a square, you can go to pretty small values of G mu. Somehow it doesn't. Okay. So the first thing I have to discuss is what kind of dynamics I will describe. So you may think that because this only has one parameter, that this is a very simple project. But in fact, the problems is in all the complicated dynamics of the network. But if you just think about one string and you say, what is the action that I should write for this string? The easiest thing to do is to do the number of the action, which is the one written here, which again has this parameter mu, which is the energy per unit length or the tension, and this gamma, which is the induced metric on the wall sheet. The nice thing about this action is that it can be integrated, and you can find general solutions for the evolution of wiggles on a string or for a loop, which are written in terms of this two vector functions a and b, which should be a function of u and v, which are basically describing traveling waves in both directions of the string. Now, this is a very good approximation for the evolution of the strings, as long as the radius of curvature of the string is very large compared to the thickness of the string. And this is what I'm going to take as my dynamics for strings. Of course, there are moments on the evolution where this is not true, where the radius of curvature is going to be comparable with the thickness. And at that point, you can have, for example, some energy radiated, as people have discussed already. I will neglect, for most part, those contributions. Now, the other thing that I need to know is what happens when the strings interact. And also, this has been discussed before. This has been simulated a long time ago by Paul Scheller and other people. And they found that basically this type of process occurs where strings exchange partners and they produce loops. This is crucial. This is very important for the network to survive as a viable model for cosmology, because this is the mechanism by which the network of the string loses energy, right? The network produces these loops. These loops, remember, have some tension, and this tension makes the loops oscillate, in fact, in periodic motion. And therefore, this huge amount of energy oscillating basically radiates all this energy into form of gravitational waves. So as I said, it's crucial because it's very important for us to have a viable model for a network of strings, but it's also crucial for me because this is the actual signal that I'm interested in for this talk. So loops are very important. Okay, so how do I go to the next one? Here you go. So what I want to compute is the a stochastic background from the whole network. This sounds like a complicated project because you need to integrate or perform this integral that is written here that people have discussed already before too. And it has basically 3 ingredients. This is the typical parameter that people use to parameterize models of a stochastic gravitational backgrounds, which is the NA density in gravitational waves as a function of frequency. And this is computed with this double integral. And the ingredients that you need are, first of all, you need some cosmology. And here I'm not going to be, basically, I'm going to be very conventional. I'm just going to take the usual cosmology, basically a radiation dominated the universe and then a matter dominated universe. And the number of degrees of freedom are just going to be the standard model degrees of freedom, nothing special there. People have assumed other possibilities and they are also interesting, but for my talk, I will not consider them. The other ingredient that is obvious is that you need the number density of loops. What is also important is that you need the number density of loops at all times. So because this network is evolving and is producing gravitational waves and they basically accumulate and we observe them today. But also you need this number density as a function of the size of the loop at each moment in time. This is important because depending on the size of the loop, the typical gravitational wave that is going to produce is going to change. Now, this sounds like a very complicated project, right? Because you need to know the distribution of all the sizes at each moment in time, okay? So, of course, simulations will help, but the reason why simulations are really helpful is because we have this scaling regime. The scaling regime is a moment where the network enters a regime in which all the statistical properties of the network basically scale with time. Therefore, if we reach numerically, by doing a numerical simulation at a short cosmological time, if we reach this scaling regime, we don't need to do any further because from that point on, we can assume that this scaling regime will tell us everything into the future, right? So this is a very, very important trick for us for making simulations that are actually useful. Okay, and the last step that I need is the actual spectrum or the average or typical spectrum of a loop, the spectrum of gravitational waves, okay? Now, apart from cosmology, which I said that I'm going to just settle to the conventional one, the other ingredients I'm going to be using numerical simulations to extract information from them. So in order to do the first one, I need to evolve a network. I'm going to be evolving this in an expanding universe, starting from initial conditions that look like this. Here, what you see is initial conditions, which I color each of string by its length. So you see one blue, you should see, I guess, one very long string, which is blue, which goes many times across the box. And then other very or smaller loops that you can see there. So these are the initial conditions. So I put them in a computer in an expanding universe, and the only other thing that I do is evolving with the Nambu-Goto dynamics. When the strings intersect, I allow them to produce loops, and from time to time you will see a loop changing section of the string changing color because it becomes a loop. Another very important ingredient is that when loops are formed, some of them, a small fraction of them, will enter a non-self-intersecting trajectory. This is crucial. Non-self-intersecting trajectory, because the loop trajectory is periodic, will stay there forever, right? Oscillate many, many times. Because the power of the coupling to the gravitational waves is small, it would oscillate for a huge number of times. Now, in our simulations, what we do is after they evolve a few times, we remove them from the simulation because they are not doing anything except just oscillating. We tag them, we put in a file so that we can study the size, their sizes and their properties and when they were produced at each moment of time. Okay, this is simulation again. So thanks to this simulation, we can we don't have to sort of guess what the sizes of the loops are or what is the number of loops that they are. We can actually compute it. We can actually compute it directly from the simulations. Once we get to this scaling regime, we can compute what is the distribution of loops that are produced in this scaling regime. So the number we can integrate this production, some people refer to this before as the loop production function. We can integrate it to get the number density of loops, which in this particular case, I'm giving you here the number density of loops in the radiation era. So this coefficient is basically important because it allows you to set the actual value of the density at each moment in time. As I said, we don't have to guess what the sizes of the loops are. We get a distribution of loops, okay? We have starting from most of the loops at larger scales, meaning like the 10th of the size of the horizon, which is what people referred to in the past as alpha being 0.1. But we also have a sort of a tail distribution of smaller loops. So from here, we can now obtain the number density at any moment in time by just assuming that the length of the loop is just decreasing by emitting gravitational waves with this power, gamma g nu. And I'll have more to say afterwards about what gamma is here. But you can take it as just a number of the order of 50. Now, a couple of warnings from the simulation. You can do many things, but you need to do a little bit of extrapolation. No matter what extrapolation you do, any extrapolation should conserve, or any model should conserve energy. What I mean by this is that the amount of loops or the amount of energy into loops that you are going to consider at the end cannot be larger than the total amount of energy that you have in the long strings, okay? That's one important thing that you should satisfy. The other important thing to know is that to get to this scaling regime, we need to evolve simulations which are much, much larger than the one I show you. In fact, not one order of magnitude larger. The boxes have to be 2 orders of magnitude larger. This is just saying that the scaling regime is not cheap. You have to evolve for a huge amount of volume to get there. If you don't get there, you are basically in a transient regime and you may not get the right scaling distribution. All right, so from here, we learned that we can obtain the number density from the simulations. What about the power spectrum? So the power spectrum it's important because the different shapes of loops evolve and emit in different ways. For example, if you have a very smooth, if you have a very smooth string, this string may have these cusps, which are points of along the evolution of the loop that move at the speed of light. And those points emit gravitational waves with a power spectrum which declines pretty slowly. If you have kinks, and you have kinks all the time because you have intersections between the strings, then the power spectrum would be different. So if you want to compute the final result of what is actually the power spectrum of the whole stochastic network, we need to know which one is the dominant one, or is it both of them, or what? So the good news is that we can do this from the simulations as well, because we have the loops. We can extract the loops, as I told you before. From the simulation, we can extract it. And this is a movie of one particular one, that, a random one. So you learn several things by looking at this loop. The first thing you learn is that the evolution is quite complicated. It's not just it's not like a circle or some modification of a circle. It's a complicated dance of different parts of the string, whose tension makes them collapse, but not at the same time, and therefore they avoid each other, allowing the possibility of these non-self-intersecting trajectories. As you see, this is periodic, as it should be, and is not particularly smooth. Okay, it has a lot of structure. This is because this loop has been produced out of the collision of many long strings. So this is the many generations below the initial conditions loop. So we can take this loop because it's a source, put it into Einstein's equations, linear Einstein's equations, and obtain the gravitational waves that it produces. But this would not be the right thing to do, because as the loop evolves, it emits gravitational radiation, and therefore it changes its shape. So we need to take into account back reaction. So one way that you can take into account this back reaction is something that we did a few years back, which is to consider that back reaction works by smoothing. So as the loop evolves, we can take the original loop over here and then say, well, what about if we just smooth a small scalar structure of this loop? How does it look like? And this is this one. We take more, a bigger, larger scale of the smoothing, you get this other loop. If you get a bigger one, you get this other one. So you see each loop becomes smoother and smoother. Now, one interesting thing, a very important thing that you see is that these loops do not self-intersect because you smooth them out, okay? It could be, we didn't know this before we did the simulation, it could have been that by doing a small smoothing, the loop would just collapse and breaks into pieces. If that would be the case, then the result would be very different for the network, okay? So this is the first step that we learned from here. The second thing is that we can actually compute the power spectrum from all these smooth loops. So we took 1,000 of these loops, we averaged the power spectrum produced by them, and we got this sort of smooth picture. Okay. So with those two things, now we have all the ingredients. We can calculate the final expression for the stochastic background, which is given here. It's a picture that people have shown before. So again, this is the any density in gravitational waves as a function of frequency. And I'm plotting in gray different values for the stochastic background for strings of different values of G mu, starting at 10 to minus 9, the largest one, and going to 10 to minus 23 at the smallest one. So the first thing you see in this picture, so these ones with color are, this is the bound from pulsar timing array. This is LISA, BBO, and LIGO. So you see that the strongest bound comes from pulsar timing array, and it sets a scale of the order 10 to minus 11 for G mu. So one thing that you see is that pulsar timing is more competitive than LIGO, that just does not have the sensitivity to get there. This, by the way, these expressions, as Laura was saying before, is quite easy to understand as the production of loops during the radiation era, which is in this part. And the bump over here is produced by the loops which are produced in the radiation era, but they are emitting during the matter era. Okay. So from this picture, we see a few things. The first thing is, as I said, pulsar timing array is the most competitive thing now. But the good news is that because this spectrum covers so many ranges of frequencies, if we discover something, as I'm going to discuss in a little bit more about this pulsar timing array data, if we discover something now, we may confirm it by later on by looking at LISA data. Okay, so this is something important to keep in mind. So from this picture, we derive different values of the constraints of G mu, which come from either pulsar timing array, or if you go all the way to LISA, you get to very low values of G mu, which are 10 to minus 18. Now, the important thing is that with these values of G mu, you will not see these strings in the CMB. These are two small values of G mu. The perturbations that these strings would produce in the CMB would not be visible. Okay, so this is taking into account this toy model for back reaction. We need actually to do real back reaction because, as I will describe in a minute, it is actually very important to get this right. So what is back reaction here? So as I mentioned before, the number action gives you this simple solution for the position of the string. Now what we want to consider is the correction due to gravitational effects. Okay, this is some sort of force that you have on the right-hand side. This is a linear correction of the G mu. Remember, the G mu is small. So we can take this into consideration to see how the loop changes. Okay. So we've done that with the loops that I was telling you before, with some of the loops. And this is one particular one. This is preliminary results, so we are not done with this yet. So you take the original loop that I said before, it's just a periodic solution. And now what we do is we apply this real back reaction in such a way that, go to the next slide, if I can. Here we go. And here you see that what we have done is to evolve this Nambu-Goto action with the correction, with the back reaction correction. And you see that part of the loop has been smoothed by this correction. In fact, if you pay attention at the beginning of this, what you saw was a tiny bit of loop being emitted here, right? So part of the back reaction also induces the production of loops. But it seems so far that the evolution of these loops, even with this real back reaction, does not lead to any sort of cascade of more loops production. So this is a more evolved loop when the loop has lost even more energy. So you see it's even more, it's smaller, has less energy because of the back reaction is basically due to the gravitational radiation, but it also has a smoother. So you can compare here the three shapes. And you can see that in some sense, this real back reaction smooths the loops. There's less smaller scale structure in this loop on the right than the one on the left. But in fact, looking at this in detail, real back reaction is more than just the smoothing. Okay, and this is important because we can now compute what is the power spectrum emitted in each mode for the different loops. For the original one, the blue one, for the one that has 50% of its energy, for the one that has 33% of its energy. And you can see there is a change. This is only for one loop, so we don't know exactly what is the effect on the average of all the loops. But we do see that there is a change in the spectrum. So why is this important? So people have alluded to this nanograph 12.5 year data, where basically a nanograph, people gave some contour plots for this parameterization of the signal as the amplitude and the slope of this strain. And people have discussed the possibility that this signal was produced by a network of cosmic strings. Some of the people have already discussed this today. So what I want to emphasize is the back reaction is very important to this comparison. And for this, together with Ken Nolan and Jamie Walker, we studied the effect of changing the spectrum. And here we look at the spectrum produced by these smooth loops that I talked before, or by a spectrum which only produced by cusps, only by kinks, or just everything in one mode. And then we put the results of this in this graph of the amplitude versus the spectral index. You see, all these graphs are similar, but they are not quite the same. So the region that they cross, let's say 1 sigma level of the data is quite different. So if we want to pin down the model of the string, we really need to know the power spectrum in detail. Okay, this is quite important to compare to data. All right. So as I said, we need to do real back reaction because we need to know how does this picture changes. The picture is not going to change much by back reaction in this high NA plateau. The reason is that no matter what power spectrum you get, you're gonna get something here which is independent of frequency. But the curves would change around the bump, okay, and the slopes would also change if you change the power spectrum. So this is really important to pin down. Also, it's very important to know if back reaction changes completely the picture, meaning that it's going to change, and these loops are non-self-intersecting, are going to break into a lot of pieces. Furthermore, it's also important to have back reaction to know how many cusps you would have on a typical loop. Okay, all these things are related to one another, and all these things we will learn by taking the loops on the simulation and doing individual back reaction for all of them. This is very time consuming. We wrote a code to do this, and we are in the process of analyzing the results. So I think I'm close to my time. So let me just conclude by saying that cosmic strings, as everybody in this audience knows, are predicted by many models of extensions of the standard model. I think we are entering a region or a time of precision cosmology and cosmic string simulations, meaning we basically pin down the number density of loops from the simulations, and now we should really do a careful job of computing the power spectrum. For that, we need to take into account real back reaction, not just toy models of this back reaction, because as I said, is important for comparison to the data that may be coming, for example, the data from pulsar timing observations. Now, one very important thing that I think should be stressed to not only this audience that everybody knows, but to other people interested in cosmological backgrounds, is that cosmic strings have a very wide prediction, a very wide spectrum of frequencies, and therefore it's interesting to study cosmic strings not only for PTA, but also for LISA, for future detectors. Okay, so I think this is something that is different from, for example, other models like bubble collisions or phase transitions. And hopefully, as we learned today also, all these bounds will have an impact on our knowledge of the high-energy physics in the early universe. Okay, and I think I should stop here. Thank you.
Thank you very much, Jose Juan. Time for questions. I saw that Kai wrote on the chat one question, and he's also asked the hand raise. Please, Kai, go ahead.
Yes, yeah. So thank you very much for this very interesting talk. I think I learned a lot. So first of all, I think you mentioned this before. You mentioned this during the talk, but I guess I missed the crucial piece. Can you remind me again why the solution for the cosmic string loops leads to loops that do not intersect with themselves? I mean, I understand that you find a periodic solution. I understand the effect of back reaction that you mentioned, but what would be the physical or the intuitive reason that these loops do not intersect with themselves?
Well, yeah, I didn't mean to say that this is the case. And typically, any loop that you would draw in a piece of paper or initial conditions that you put in the computer will self-intersect. So most of them, the vast majority of them, will self-intersect, and we understand why. The reason is because a loop has tension, so it wants to shrink. It wants to shrink, has more possibilities to self-intersect, right? So why are there non-self-intersecting loops? The reason that they are there is because those trajectories exist, and the network has millions and millions of loops. So by try and error, it tries many times and eventually finds them. So our code identifies those loops and then takes them out. But a loop is, a loop as it is produced from the network, it will self-intersect many times. So that's why I was saying that, that's why I show you this particular loop. It has a lot of structure, because this loop is not a loop coming from the initial conditions. It's a loop that has encountered many strings in its path to this non-self-intersecting trajectory. So in some sense, it's natural selection that produces these non-self-intersecting loops. You produce many of them, and a small percentage of them have the right properties to be non-self-intersecting.
Okay, yeah, thank you very much for clarifying this. I think this was the one piece of information that I was still missing. Maybe I can also just ask you a very quick technical question. In your expression for the gravitational wave spectrum, you put this ratio of scale factors, A at the time of formation over A today to the third power. I was wondering whether there shouldn't be a fourth power, because the gravitational waves, they redshift like radiation.
Well, maybe I made a mistake, but
yeah. Anyway, yeah.
I think it's correct. I think we've done this many times. I guess there are several instances in which these scale factors enter. Yeah. One is the NA density. The other one is the frequency is redshifted.
Right. Yeah, yeah. No, I just noticed this because I had the same expression on my slides and I had a different power, but I think it can also be hidden in the dp over df. Yeah, so it depends on how you write it down.
It depends how you write it down. Yes.
Yes. Okay. Thank you.
We have one other question by Tammy Vasespati. Please.
Hi, Jose. It's yeah, it's a very nice talk. I actually had a couple of questions. So when you showed these the PNs from the smooth loops, you didn't say what the power was. So
sorry. Here?
No, no. After you've done back reaction. So remember, you have 3 plots, 3 curves. Yeah. Here. So is this n to the minus? What is this? N to the minus 1/3 or? Oh, sorry.
You mean the what is the scaling?
Yeah.
I haven't looked at this yet.
Okay. All right.
But,
The other.
my guess is that there may be some cusps at the end too, because these are pretty smooth things. But
I see. The other question actually ties in with Kai's comment, which is that have you looked at how the angular momentum is radiated? Because I think that's what is stabilizing those strings.
Right. Yeah, we look at the angular momentum from when we did the smoothing of the toy model. And right, I don't remember. I think we got some sort of broad peak on the angular momentum of all these loops. But they were already not self-intersecting to start with. So yeah, I mean, if you take a random one and compute the angular momentum and compare it to the one that is not self-intersecting, probably there's a big difference, yes.
Okay, thanks.
But of course, another interesting thing would be what happens to the angular momentum to the non-self-intersecting ones when you take the real back reaction into account. And this is something we will definitely look at.
Okay, all right, thanks.
So we are running a bit late. Since we have a lot of time for discussion at the end, probably it's better if we leave the remaining questions for the discussion session. Please write them on the chat so that we have them for the discussion session at the end. Now I leave to see, again, we are running a bit late. I leave to the organizers, since it's a break now, to gauge the quantity of the break.
Yes, and thank you, Jose. So I'm afraid we can only afford like 6 minutes. So we meet at 4:30 European time. And just a request to all the speakers again. So kindly, if possible, be present during the discussion session, and which will be scheduled, which is scheduled at 6:10, but probably it's going to be a little bit late, like 10 minutes. Okay, thank you. So we meet at 4:30 European Central European time.
Thank you very much.
Hola, Ana.
Hola, ¿qué tal?
Bien, bien, bien.
Estamos saliendo con Maya.